Hello, today I'll be talking about this work of beating classical impossibility of position verification. This is joint work with Jiahui Liu and Qipeng Liu. So let me begin by introducing the task of position verification. So you can think of the task as being having a prover who wishes to convince the verifier that he is at a certain position. So for this talk, we'll think of the prover being an astronaut and the verifiers being people on the Earth. So one thing we can do is called distance bounding, which informally is the following. So a verifier being on the Earth wants to know where the prover is. So what he could do is to send a message. And if the prover responds within a certain time, then he is certain that the prover must be within this region by no faster than light communication principle of special relativity. So in order to improve the precision, what you could do is to just have multiple verifiers and repeat this process. And then you can, at the end, triangulate where the prover is. But the issue with this approach is that if there are multiple provers or there are multiple adversaries and they are colluding, then they can actually incorrectly convince the verifiers that they're at an incorrect position. So in this example, they can convince the verifier that they are at this location, while in reality, one is over here, one is over there, and none of them are even close to this position. So in general, let's focus for simplicity's sake, let's focus on one-dimensional, and we are going to consider something like a Minkowski diagram. So the horizontal axis represents the location or x-axis, and the vertical axis represents time. So time goes on as you go up. And furthermore, messages travel at speed of light. So in general, let's say there is a prover and there are two verifiers without loss of generality. And the prover wants to convince the verifiers that he is at this certain location. So without loss of generality, we can assume that the protocol looks something like this. The verifier on the left is going to send some message. And the verifier on the right is also going to send another message. And the timing is made so that these two messages arrive at the prover in the middle at the same time. So the prover in the middle, upon receiving these two messages, is going to compute some function that is a function on both M0 and M1, and then spit out the response to both parties. And at the end, these parties are going to check whether they get the correct response R. And unfortunately, even for something as generic as this, there is also a generic attack that attacks this position verification protocol. So think of the following scenario where there are two adversaries, none of them are in the middle, and their goal is to compute R on each side, and while the timing constraint is such that they only have one round of simultaneous communication. Unfortunately, there is a very natural attack to do, which is that the adversary on the left, upon receiving M0, is going to remember M0 for himself, and at the same time, send a copy of M0 to the adversary on the right, which corresponds to this error. And similarly, for the adversary on the right, he can also do something similar, which is keep M1 for himself and then send a copy to the adversary on the left. And then after one round of communication, they both know M0 and M1 and therefore can compute R. And furthermore, so first let's observe that this attack is actually very efficient. In fact, it's as efficient as what the honest prover does. And furthermore, even if f is designed to be a randomized function instead of a deterministic function, you can still de-randomize this process by having these two adversaries sharing some randomness. And then this f is essentially de-randomized to be a deterministic function, and the same attack goes through. And furthermore, because it's efficient, even if you consider computational assumptions, you still cannot get around this impossibility. Okay, so the impossibility I mentioned before is given by this work by Chandran et al. In 2009. In that work, they also consider constructing a protocol against a bounded adversary, in particular bounded storage adversaries. And after that, basically all non-position verifications that achieve security against colluding adversaries they all use the power of quantum. In particular, they use quantum communications, starting with the work of Kent, and there are a long list of work that that this list is not meant to be complete. So in this talk, what we construct is that if we assume that learning with errors is hard against quantum computers, we construct position verifications against quantum adversaries, but the protocol is classically verifiable. In particular, this means that the verifiers are entirely classical. In particular, they don't possess any quantum computation powers, and the protocol is classical communication. So the verifiers only needs to send classical messages and receive classical messages. So a natural question is whether we can do better. Unfortunately, we also show that for a classically verifiable protocol, you must have a quantum prover. And in particular, this kind of protocol would also imply the existence of what is known as proofs of quantumness. And therefore, you also have to assume some computational assumptions. You cannot construct unconditionally secure position verifications that are classically verifiable. So before I go into the construction, let me first motivate why it is a good idea to have classical communication or classical verifiable position verifications from a practical perspective. So the most important thing is that for position verification, the only reasonable model of communication is wireless communication or free space communication. And a feature of free space communication is that they inherently have a high loss. And this is especially an issue when you are sending quantum messages due to the intricate nature of quantum states. So starting with the work of Qian and Siopsis in 2015, they show that non-quantum position verification protocols actually break down when the loss is high. So in particular, this means that either they lose completeness, which means that the honest prover can convince the verifier, or soundness, which means that colluding adversaries cannot beat the position verification protocol. Okay, so following that work, there is also a few works that studies loss tolerant quantum position verifications, where they reach the they essentially raises the threshold in which for which the position verification protocol will still work. Furthermore, there are also these two works showing that showing protocols where they achieve full loss tolerance, but the security only is their protocols are only secure if the adversaries are unentangled. However, you can notice that all of these issues would be non-existent if we only consider classical communications, because for classical communications, we can simply repeat the message multiple times, and this will not introduce any intricacies in the security argument. And therefore, a corollary of our work is that we actually achieve full loss tolerance position verification protocols even against adversaries that are entangled. Although I will not explain how to achieve security against entanglement in this talk. Some further motivations for getting classical verifications include that if you think about free space quantum communications, they usually use a tracking laser to make sure that they're sending the message to the correct space or correct location. And this is something that is not very efficient. And again, for classical communication, you don't need this kind of accuracy. And finally, if your protocol is has quantum communication, then it might be harder to compose your protocol with other things that you might want. For position-based cryptography, for example, you might want to authenticate the message. And this becomes a little bit harder and a little bit more subtle when you're considering quantum communication. Okay, so let me talk about let me talk about how to get quantum position verifications with quantum communications as shown by previous work. So let's go back to this diagram. So the prover is in the middle, and now he instead has some quantum device. Here I'm considering something that is a measurement device that measures a photon. And so this protocol that we'll be looking at has the particular property, which is that there is only one message that is quantum. In particular, the first message sent by the verifier on the left is going to be a single photon that encodes a BB84 state, which essentially is one of the 4 possible states, which we'll denote as 0, 1, or plus or minus, or h of 0, h of 1. So in other words, you can encode one of these 4 possibilities by 2 bits, one bit being B, the other bit being theta, theta denoting the basis that the bit is encoded in. And so this is the first message, and the other message sent by the verifier on the right is the basis theta to the prover in the middle. So the prover in the middle, upon receiving the basis theta, he is going to measure this photon at the same time in this correct basis to recover B that is encoded in the photon. And then he is going to report the measurement results to both ends. And then both ends can check whether the prover has recovered the correct bit. Okay. So if you look at, so I'm not going to show why this is secure, but on a high level, this protocol gets around the impossibility because if you recall, the impossibility explicitly asks you to copy this message, which is that this adversary is supposed to remember this quantum state and also send a copy, which is something that you cannot do in general for quantum states. And here, they can actually provably show that because theta cannot reach the left adversary in time, without knowing theta, this state is actually provably unclonable, which in turn established that this protocol is secure even against quantum adversaries. So given this protocol, let's go back and reflect on the position verification impossibility. Basically, the way that they evade this impossibility is that is by this bubble. In particular, I said F can always be efficiently de-randomized, but here, instead of considering a classical function F, they're considering something that is inherently quantum. And therefore, it is clear that this impossibility holds only if F is a classical function. And therefore, to get around the impossibility, given this example, we know that the function F must be inherently quantum. For example, in the last example, F is taking quantum inputs. However, there is also another idea of getting a quantum function, especially if you want classical communication. Then this F is just a function, but maybe instead we need to have a classical function that is inherently quantum, which means that only a quantum computer can evaluate this function. And one idea is that maybe we can make prover prepare some computationally unclonable states, similar to a BB84 state that is unclonable unconditionally. Earlier, I mentioned that classical verifiable position verification implies proof of quantumness. And therefore, a natural place to look for these computationally unclonable states would be to look at proof of quantumness protocols. And in particular, we'll look at the protocol by Brakerski et al., which uses the following primitive, which is called trapdoor clock-free functions. So on a high level, a trapdoor clock-free function is a function that is parameterized by a public key that maps n bits to m bits. And clock-freeness means that this function is 2 to 1, and it is hard, but clock-free means that it is hard to find a collision in this function efficiently for a random public key. And the trapdoor property says that when you are sampling the public key, you will also sample a trapdoor along with the public key, which allows you to invert this function for that particular public key. In particular, for any output y, using this trapdoor, you can efficiently recover the two preimages denoted by x0 and x1. And furthermore, we will also be going to use another property called adaptive hardcore bit, which I will not introduce for now. Okay, so with trapdoor clock-free function, let's see how we construct a proof of quantumness, which is the protocol given by this work of Brakerski et al. So the task of proof of quantumness on a high level is that it is an interactive proof between a classical verifier and a quantum prover, such that if the prover is quantum, then he can convince the verifier that the prover is quantum. But if the prover is classical and the prover is efficient, then no matter what the prover does, he cannot convince the verifier that he is a quantum party or algorithm. Okay, so using trapdoor clock-free function, the protocol goes as following. So first, the verifier is going to sample a trapdoor clock-free function, and then he's going to send the public key to the prover. So the prover, being a quantum CPU or a quantum party, what he can do is to prepare an equal superposition of all the possible preimages x, and then evaluate this FPK in superposition. And in the end, what he will get is this quantum state. And then he is going to measure the output register of FPK, which gives him a classical output denoted here by y. And then he is going to send this y to the verifier. So the post-measurement state upon measuring this y, you can show is exactly an equal superposition of x0 and x1, where x0 and x1 are preimages of y. And the verifier having the trapdoor can, as we mentioned, efficiently invert y and recover x0 and x1. So the next thing the verifier is going to do is to sample a random coin theta, denoting the basis that the prover should be measuring. And in particular, if theta is 0, the prover is going to measure this state in the standard basis. Otherwise, if theta is 1, then the prover is going to measure this state in the Hadamard basis. And then the prover reports the measurement results to the verifier. And then you can see that for each of the bases, the verifier can classically check whether this measurement outcome is consistent with this state. So the adaptive hardcore bit property that I mentioned earlier can be intuitively thought of as the property that for any even quantum adversary, he cannot produce the 3-tuple y n0 and n1 such that y n0 passes the first verification while y n1 passes the second verification, simultaneously with probability much higher than 1/2. So we know how to construct a noisy variant of the trapdoor clock-free function from quantum hardness of LWE. But for this talk, it will be simpler to simply think of trapdoor clock-free functions for now. So intuitively, you can see that the adaptive hardcore bit immediately gives you the fact that this protocol is a proof of quantumness. This is because if a classical adversary could pass this test with probability, let's say 1, then you can always rewind this classical adversary and send him a different theta, in which case you will be producing this 3-tuple with y and 0 and 1, both passing the verification, which violates the adaptive hardcode bit. However, this is actually saying something much stronger, which is that this post-measurement state is actually unclonable by the adaptive hardcode bit property. The argument is very similar to before. In particular, if you assume you can clone up to some approximation, then you can have 2 copies and measure 1 copy in the standard basis and the other copy in the Hadamard basis. So if your cloning is very good, then I should be able to produce both N0 and N1 with higher probability than 1/2, which is a contradiction. Okay, so there seems to be some computational unclonability here. So let's try to use this TCF state for classical position verification. So the first attempt here is that we're going to take the BB84 based quantum position verification protocol, and instead of sending a BB84 state over here, I'm just going to sample a TCF public key and send this public key to the quantum prover. And then the quantum prover is going to do exactly the proof of quantumness protocol. In particular, he is going to produce this equal superposition and evaluate F. He is going to measure this Y and then measure this X, either in standard basis or Hadamard basis given by theta. And then he is going to report the measurement results to both ends. Actually, this protocol already seems to evade the classical impossibility. In particular, if you recall, this is the classical impossibility. Of course, you can still do the same thing as before, as these messages are classical. So this adversary can copy these messages and send them to each other. However, the issue is that at the end, because this measurement is randomized, the verifiers will see a different response with high probability. And therefore, if we add the check that the verifiers are going to check whether they receive the same response, then this seems to already evade the classical impossibility. Okay, but unfortunately, there is actually an attack for this protocol. And the high-level idea of this attack is that this adversary does not need to prepare the state honestly. In particular, what the adversary on the left could do is to actually guess which theta it is, and then prepare 2 transcripts of the execution. So in particular, he is going to guess theta is 0, and then run the protocol once with theta being 0, and then guess theta being 1 and run the protocol with theta being 1 and get another transcript. And then after 1 round of communication where the adversary on the right simply forwards theta, they can simply pick out the transcript that corresponds to the correct theta and then report the correct y ends to both parties. And this actually simulates the honest prover perfectly. And therefore, unfortunately, our first attempt is actually insecure. However, you can see that this protocol is insecure due to a very simple reason, which is that in the proof of quantumness protocol, the prover sees theta after he has sent y. However, here there is no such constraint. And therefore, if we make the prover commit to y, then maybe the adversary also needs to commit to y before picking theta, which might make this attack go away. So the second attempt is very similar to the first attempt. In particular, the verifier on the left is still going to send public key to the prover, but the timing constraint is changed a little bit so that the verifier on the right is actually going to send the theta message actually a little bit later than this red message. And then So the prover is going to receive the red message first, and then he is going to prepare this state and then report Y as before. And then upon receiving theta, he is then going to measure the host measurement state in the correct basis. So at the end, they are going to check the measurement result. So the main thing here is that the verifier is going to do another check, which is that they are going to ensure that the message Y is received before ends. In particular, this message should not depend. It should not be possible for this message to depend on the trace of theta. So it turns out that this protocol actually can be proven secure. So I'm not going to do the full proof for this talk. If you're interested, you can look at our paper. Or one of the main ingredients is what is called a computational non-local game of Trapdoor claw-free functions. So this could be understood as the following. So again, this is the proof of quantumness protocol that is forerun by Brakerski et al. And in order to make it a computational non-local game, what we're going to do is that instead of doing the last two runs, we're actually going to add, before that, we are going to add another thing, which is that we are going to ask the prover to split himself into two halves. So this is his quantum state. Presumably he has some internal state after the first two messages. We're going to ask the prover to split into two halves, and then we are going to separate these two halves physically. And then the verifier is going to finish the protocol with these two halves. In particular, he is going to sample one theta as before, and then send this theta to both halves. And then both halves is supposed to report the measurement outcome to the verifier in the middle. To emphasize here that the two halves are getting the same theta instead of two independent thetas. Of course, these two halves can be entangled, which is why it is a non-local game. And what we've shown in the paper is that the success probability of any efficient prover that is able to pass both checks is bounded by 3/4, thus negligible. You can think of it as some kind of computational unclonable property, because of course, if you can clone this state, then you can always simulate a proof of quantumness prover with basically no loss, and therefore you are able to successfully pass these checks with probability essentially 1. But the fact that this is significantly less than 1 shows that this state must be unclonable, even if the adversary could do whatever he wants, including not following the protocol. To conclude, I will mention some other results. So the protocol that I've shown before actually only achieves soundness 3/4 against efficient quantum adversaries. And we showed in the paper that you can get the soundness down to negligible by essentially parallel repetition. And the analysis is borrowing some ideas from existing works listed here. And also the security, while I did not show the proof, but it only works for unentangled adversaries. In order to bootstrap the protocol to make it secure against entangled adversaries, we borrow some existing ideas from quantum position verifications. And what we are able to achieve is that if we assume quantum LWE is sub-exponentially hard, then we get a protocol that is secure against bounded entanglement. And if you want security against unbounded entanglement, we can also get it by combining our protocol with the protocol of Unruh, which gives you security against unbounded entanglement in the quantum random oracle model. And finally, for our protocol, we also show that it is actually insecure so the base version is actually insecure against entangled adversaries. And this attack can be carried out efficiently. So finally, some future directions include that extending our work to high dimensional, since we only consider one-dimensional position verification. And then there is also seems to be some trade-offs between the attacks. In particular, if you spend exponential time, you can break any classical verification protocol. On the other hand, for our standard model construction, if you have share some entanglement, you can also break the protocol efficiently without spending exponential time. So it is interesting whether there are some trade-offs between using time and entanglement. And a more interesting question is, for our construction, we used some notions of unclonability, and it seems like as a consequence, the honest prover has to have some quantum memory throughout the protocol, and he has to keep the memory coherent for some time. So it would be interesting if we construct a classical verifiable position verification without honest prover having any quantum memory. Finally, it will also be interesting to weaken the assumption, or if we can get an unbounded entanglement security without proving the security in an ideal model. So with that, I conclude my talk. Thank you very much for listening.